and I'm going to be your host in Backspace for today. I run a design agency called The Loft, so I'm creative director at The Loft. And we have had the privilege of working with Data Science Festival on their rebrand, on the new website, so you will have all experienced the sort of work that we do. So a very quick intro to me. Thank you all for coming to help make this community such a thriving and amazing community. A little bit of housekeeping. If everyone can just make sure phones are on silent, that would be amazing. And if in your bags you'll find schedules of all of the talks, everything that's going on across the day, so that's all in the bags and the booklets. If you've got any questions at all, grab someone with a Data Science Festival t-shirt on and we'll be happy to answer any questions, point you in the right direction, so seek us out. There is free water at the back of the room. So if anyone needs to grab a drink, please help yourselves. Data Science Festival is a celebration of all things data. So we aim to connect the tech community to foster the sharing of knowledge, inspiration and ideas. And there is so much going on today. So just a reminder that all of the talks are being recorded. So if you feel like there's two that you need to be at once, don't worry, everything's being recorded. So you'll be able to watch back and catch up later on. A quick word on lunch. So this year we are bravely serving hot food for the first time. So please be gentle with us, and yeah, hopefully you'll all enjoy that. If you are looking for any vegetarian, vegan or gluten-free options, grab someone with a Data Science Festival t-shirt and they'll be able to point you in the right direction of the right lunch. And a quick thanks to our sponsors. So it's a free event, as you all know, and it wouldn't be as brilliant as it is without our sponsors. So I'm just going to say a few thanks to our wonderful sponsors, who are Data Idols, Time Extender, Starburst, Bumble, Monzo, Hymans Robertson, Mars Pet Care, we have got a few brilliant sponsors, BSI, The Trade Desk, Direct Line Group, Marks & Spencer, dunnhumby, Clio, Create Communities, and finally CodeNode, who have given us such an amazing venue. I'm sure you'll all agree, it's pretty cool. I'm going to wrap up now and get on to our wonderful speaker, but thank you again for attending Oktoberfest. We really hope you have a brilliant time today. And if you have a look in your booklets, you'll find a free pint on us. So there's a free pint in the beer garden if you want to head there later on. There's a couple of competitions that we've got going on today as well. So there's loads of DSF goodies up for grabs. So you can find those in the booklets again. So without further ado, I'm going to introduce our first wonderful speaker. So Chris Ballard is lead data scientist at Tessian. Chris is passionate about using data to make a real difference. So Chris has over 20 years experience as an engineering and data science technical leader, as a product manager, consultant and CTO. So he's worked in lots of different sectors: edtech, e-commerce, market research, climate tech and security. And in his current role, he is protecting customers from targeted phishing email attacks. Chris also has a wonderful rescue dog, Maddie, 2 kids, brews his own beer, and is currently building his own drone. So without further ado, I'll hand over to Chris.
Thanks.
Welcome.
Thank you. Okay, thanks everyone for coming to this session. So today I'm going to be talking about how we protect our customers against advanced phishing attacks, and particularly talk about some lessons that we've learned from a project that we started to use machine learning to detect those, or particular types of those attacks. Kind of agenda of this talk. I'm going to give you a bit of a lowdown on email phishing attacks, give you some examples. There's nothing like kind of making things a bit real. We'll talk about that project, detecting bulk phishing attacks. We'll talk a bit about what that means. And then we'll talk about 2 particular issues that we encountered in that project. One relating to bias in the data that we collected, and 2 around, how on earth did we measure what the performance was going to be in production. And hopefully there'll be some really tangible, sort of practical kind of takeaways that you can get from this. A bit about Tessian. What do we do? So we protect our customers from advanced phishing email attacks, and we do that in a number of different ways. Firstly, we protect our customers with our Defend product, and we protect them against inbound email attacks that they might receive, and we do that through an AI-based detection system, which is able to adapt and learn to new attack types as they happen. Conversely, we also protect customers against the accidental or malicious loss of data in emails that they send out. So you all know the kind of scenario where you accidentally send an email out and realise it's got sensitive information on it. So Protect product protects customers from that happening. We also allow customers to respond to threats that happen more quickly, so ability to kind of search through all their users, thousands of users' emails and remediate threats, take them out of inboxes. And coaching users is a really important part, training users in what phishing is and what they do about it. So we provide very targeted information to users to help them learn about the threats that we detect as well. Email is quite hard to secure. So on the left-hand side, everyone's quite familiar with spam. There's a kind of typical sort of spam email that you might get. On the right-hand side is an example of a targeted phishing attack, though. It comes from the sender, Lisa, who works for First Corp. First Corp happened to be a vendor of Frederick's company, Acme, I had to choose that company name. And they are, supposedly informing them of a change of bank details and want them to use that link to make payment. And they've got some urgency around, we'll suspend your payment if you don't do this. That link happens to be malicious, consequences, potentially dire consequences if they do that. So our system uses a number of techniques to detect those kind of emails. We use behavioural analysis, so we look at the whole kind of network around communication patterns between users internal to an organisation and external. We look at the content, so we pick out kind of use of urgent language or terms that might be associated with very sensitive kind of topics like wire fraud or something like that. We detect kind of obfuscation. Attackers try and hide the fact that their email is malicious. And then we have a global threat network. We use the information across all of our customers to help identify attacks. Some examples for you. So very recently, this is one to look out for, the use of QR codes has become a real thing with malicious emails. This is a typical example. You receive an email, it looks like it comes from Microsoft, and it looks like a file share email, and it's got a QR code, and it kind of relates to some kind of payment or invoice or something like that. That has a malicious link behind it. Another example, more textual one. Another one looks like it comes from Microsoft. This is a credential phish. So your password expires. Click on that link. Takes you to a impersonated login website. Collects your password. Job done. Interestingly, one thing I found really interesting, which I noticed the other day, that Microsoft logo isn't an image, it's a set of HTML divs that are designed to look like the image to make it really hard to pick up on that logo. Super interesting. Okay, so a couple of examples for you, and I'll give you one other in a moment. So moving on, bulk phishing attacks. So we're always very pleased when we, find those kind of targeted attacks for our customers, and they're usually the kind of attacks that could cause, serious reputational or financial damage to a customer. But there's no denying that under the surface, there's a whole swathe of perhaps less serious threats, but nonetheless lots of them. And because there's so many, the threat is very real to customers. So these are what I would call bulk phishing attacks. So emails sent out by a malicious actor in bulk, generally not much difference between them. Might be a bit more generic, like that one. You've probably all seen those kind of examples. We set up a project because we realised from information that we collected from our customers that although we were good at detecting those very targeted attacks, and the system had been designed around that, we were missing some of those bulk phishing emails. And our objective was to try and improve the detection of those for the emails that we were not catching. And we wanted an ability to retrain the system regularly to adapt it to new threats. And our kind of technical objectives were to classify whether an email was either malicious or whether it's safe. And we wanted to do that entirely on email metadata at the time. Data that we extract from the headers and other content in the email. We wanted to make sure the precision of that model was in line with our kind of minimum requirements for production, so that we don't generate too many false positives. And you'll see this a few places. We talk in terms of flag rate, so how many per million emails do we flag, because we have a guide as to what is a reasonable number. We wanted it to flag somewhere in the region of 200 per million emails. So if you've come to this talk kind of expecting to hear about latest and greatest kind of LLMs or approaches like that, I'm sorry to disappoint you, I'm not going to be talking about that. I'm going to be talking about some very basic challenges that we face that actually are the same challenges that you would have whether you were training a cat boost or XG boost model, or whether it was an LLM. It's exactly the same issues, and we have the same issues with all of those types of models. But a little bit about the model. So we're generally taking information from, as I said, email headers, and using those to create what we call stateless features. So those features just relate to that email on its own. We take information from the email body that we parse, so presence of kind of keywords, things like that. And then our global threat network, so things like a score that we can generate against the domain of the sender. And we call those stateful features because they vary, if I don't trip up, they vary over time. And our objective, as we said, is to classify a positive class, malicious, or a negative class, safe. So obviously, as this is a classification problem, we need labels. And where do we get those labels from? So we're quite fortunate in that when our system flags an email to a user, that user or the administrator is able to confirm whether it's either malicious, whether it's safe, or whether it's spam, using kind of functionality like that you see on the right-hand side. However, we only get those responses from users, well, between 3 and 4% of all flagged emails. So it's quite low. Another source of emails is false negatives that get reported by our users. So we want to know about emails that we miss. And administrators of the system, if they're notified through their organisation of a phishing attack, they can notify us by reporting that false negative as well. So those are our primary sources of labels. So what does that look like in terms of the sort of collection flow for how we get that data? So for emails that our current system flags, if it's got a response, then if it's labelled as malicious, we can take that as a positive example. If it's labelled as safe, we can take that as a negative example. And for false negative reports, we can also take those as positive malicious examples as well. However, one really key point to note is that those are just for emails that our current system flags. A bit more about that in the moment. So we also have a whole lot more email data for emails that we didn't flag, and we don't know what the label is. We don't know whether it's positive. We don't know whether it's negative. And we also have the same for emails that we did flag that we never got a user response from. So that's got an unknown label as well. And we sample, because this volume is extremely large, we sample those emails and take quite a small sample of that in our training data. We have challenges around label noise, significant challenges. Users disagree. Labeling emails is very subjective. It's surprisingly hard sometimes to tell whether something's spam or malicious, or even whether it's safe without kind of contextual knowledge about the email. And so users disagree. And about 20% of emails have kind of multiple user labels, so the same email that got sent to multiple people. And our current technique to deal with that is by majority voting those labels to decide the most likely one. There's also bias in what the admins tell us as well. So sometimes admins label differently to users. About 10% of safe user labels mismatch what the admins said. Can be quite hard for the user who's not an expert to know. And a tendency for admins to focus on the most important ones, so the emails that our system quarantines that it's like super sure about. And we tend to say, if we've got an admin label from the administrator and we've got user labels, we'll take the admin label because it's the most reliable one that we can take. Class imbalance, as you'd expect for this kind of problem, is an issue. But it's particularly an issue because the class imbalance between the data the label data and the production data is significantly different. So in our training data set that we've collected those positive and labels for, there's about 50-50, something like that. And we also have maybe about 25% of data has been flagged, and about 3/4 of it, we don't know what the label is. Whereas in production, we flag about 500 per million emails, and the rest are just not flagged. So significant difference in terms of distribution. And our objective for our model is to try and identify this kind of subset that's sitting here. We want our model to flag those. Whilst you're looking at class imbalance of about 50% in the training set, in our in production it's a lot lower than that. And our general guide, a key point is we don't know what the recall is. So, and our estimated guide is usually a prevalence of positive emails of about 1,000 per million. So we're probably missing 500 per million, something like that. So maybe we want our model to flag, somewhere up to that, and we'd be doing a good job. Important metrics for us, I've just said recall we can't measure. Precision, super important. We want to minimize false positives because, too many false positives, you get user fatigue. They'll stop bothering labeling emails because there's just too many. Particularly important with certain types, categories of warnings that get generated a lot. Flag rate we've just talked about, and we also continually monitor how good are we catching emails that we missed before, so we can track our improvement over time, which is an important business metric for us actually. Okay, there's a lot on this. I'm not really going to focus on too much on here, but that bias in the data is a significant problem. The key one, there's lots of sources of bias. The key problem is that those labels are only for emails flagged by the current system. That's problematic because obviously those emails are selected because our system in its current algorithms decided it should be flagged, and then add to that the other bias of the way that the labeling is done. And that has an impact. So for positive emails, you're only seeing positive examples for certain types of malicious email, and it excludes those ones that we want to train our model to catch, potentially. And negative ones, it's going to be biased towards false positives that we've mistakenly flagged. And so therefore there's going to be certain characteristics of those emails. So those cause challenges. We have as you saw in that, training data set, the different types of emails that we've got there. We've got a lot of those non-triggered emails that we never flagged on. And we could make a naive assumption that they're all safe because actually the prevalence, the percentage of real positives in there is extremely low. But that will mean if we evaluate our model against those, any false positives, they could actually be true positives. So we have to be a little bit careful with that. So the impact on that on terms of modelling is we end up training a model that detects emails that were flagged by the existing system. In the early iterations of this model, we found we were overfitting to that, and it became extremely good at classifying emails we already knew about, but worse when we're classifying new emails, and we had to set extremely high thresholds. And the confidence score the model was giving was a bit unstable at the top end as well, to reduce the false positives, which obviously reduced the effectiveness of that model in production. Over time, we realised actually we had a very nifty way to overcome some of those issues with bias, and that is by using something called deny listing. So one of the techniques that we have in the system is the ability to use a threat feed. So a threat feed will tell us URLs and domains that are known active threats that are out there that have already been recognised. And the way we use those in the system is we'll run an email through our detection algorithms, and if that doesn't flag any of those, we'll then run it through a threat feed, which may well flag it. And actually, those are really good examples of emails that we really want our new model to catch, because we want to catch them before they ever get to that stage. So therefore, we can use those deny-listed emails or emails that have characteristics like a URL on them, that means they're in a deny list, to do things like tune the model to be better at detecting those. And potentially it's not reliant on user labels as well, because we can do kind of majority voting across multiple deny lists from different providers as well. The downside of that approach is it will have a tendency to only include emails that have got URLs in them. So slight downside. We talked about false negatives. That's also another way of countering that selection bias that we've got in our training data as well, because those are genuine examples that we want our email to see. But the volume is extremely low in comparison. So you're talking kind of at the moment kind of several thousand. So we adjust our data set, and we can adjust it to include those false negatives and deny-listed emails as examples of positives. And we can also use those deny-listed items in our validation set, use that for hyperparameter tuning. And then in our test set, with our second, I suppose, iteration of the process, we could then include our unlabeled email, a sample of unlabeled emails in our test set, and through manual labeling of a small sample, get an estimate of what the ability of that model would be to detect new emails. We could also do something about, if I go back to the previous slide, could we make use of these? Because they're high in volume. Initially we took that naive assumption that I talked about earlier on, that let's consider these safe and see if that is a helpful thing to do. And now there are other ways that you could deal with that. You could deal with that through semi-supervised techniques, things like that. So there are other ways we could treat those, but starter for 10 is to treat those as safe examples. With that in mind, let's just take a step back and think about, okay, if we were training this model, testing it, what is our decision process for deciding whether that model is suitable for putting into production? So we have to go through a whole number of steps, including that manual labeling. But the problem is that because of that difference in class imbalance between test set that we've got and production, we weren't very confident that the precision we were measuring would be representative of the precision in production, and we needed to be sure of that. So our practice would have been, well, we'll deploy the model, we call it silent. It would be like a kind of canary deployment. We run the model on production data, but the user never sees the results of the model. We take a couple of weeks to collect enough data. We manually label a sample, and then we decide whether it's good enough. But that whole process takes like a month. It's too slow. So we needed a way to overcome that. And we started to think about, is it possible to estimate what the precision of that model will be in production based upon the precision that we've measured on our test set. Now, I'm sure everyone's familiar with precision. Precision being true positives divided by the number of true positives and false positives. You can see that because that takes into account the number of actual examples, if our class distribution changes, it changes the precision. So you have to be super careful of that. It's easy to forget that when you're comparing different data sets and measuring precision. And especially in that scenario, so our actual test data set had what I would call positive prevalence of 14%, but in production it's significantly lower than that. So the impact on precision is going to be fairly extreme. One of the ways that we could deal with that is to think in terms of false positive rate and true positive rate, because those are invariant with class ratio. And let's introduce a kind of parameter, eta, which is bounded between 0 and 1, which is our prevalence of positive examples. So it's in comparison to negatives. So it's the sum of the true positives and the false negatives divided by the total number of negatives. And those are our standard kind of expressions for true positive rate, the fraction of true positives out of the total number of positives that we've got, and our false positive rate, fraction of false positives out of the total number of negatives. And we can actually derive an expression for precision in terms of true positive rate, false positive rate, and that positive class prevalence as well. So what that means is we can use that expression to plot precision recall curves to estimate what that curve would look like for different positive prevalences. So these charts show on each chart two curves, and these are two different versions of the model that we were testing, version 4 being the more recent one. And that's our result on our test data set. That's the result if we were looking at a positive prevalence which was similar to production, and that's what it would look like if it was what we think the positive prevalence is in production, that 1,000 per million. So we can see, our curve looks brilliant up there, but it's actually looking, pretty terrible down there. What do we do about that? So one of the things we can do is, let's threshold our model, and we'll take a threshold that gives us a precision that we might be looking for. And if we threshold our model, that will give us a certain fixed true positive rate and false positive rate. False positive rate quite low because the number of negatives is fairly large. And one of the things we can do is we can plot how the precision varies as we adjust the positive prevalence in the data set. And that's quite a useful diagnostic tool we found, because we can use that to start looking at what's the range of precision that we might be interested, or we might be looking at for what we think the prevalence of positives is in production. So if we're looking at somewhere between 1,000 per million and above, we'd be looking at somewhere in the region of sort of 30%, but it could be somewhere up here, because we don't exactly know what the positive prevalence is. So how does that compare to? So fast forward, we've deployed the model, we've been running it for a month. How does that compare to what we see in production? So this is a screenshot of a dashboard that we use to monitor the system. So we have automated dashboards in place to monitor metrics from our models and the responses that we get back from our users. And I think, if memory serves, this is data over 30 days. So it tells us, this is in aggregate, not just for this model, how many flags did we generate? That's the total number of emails that we checked. Is that about 1 billion? Yeah, about 1 billion. And that's our flag rate, and we can look at the distributions by tenant to see whether we've got by customer, so we can see whether we've got any outliers. And this is our model that we were just talking about. And based upon about 5,000 responses, we're seeing a precision of about 70%. What that means is, actually, if maybe our positive prevalence is a bit higher than we thought it was, but it seems like this could be a useful technique to give us a guide as to what that precision would be. So what that means is we cut time on deployment. If we have some confidence that that precision, the precision that we estimate is reasonable, and we use that diagnostic tool, we can start to make some decisions more quickly about whether we can launch in production. And that's really important, because if we need to introduce new features to adapt it to new threats, we can do that much more quickly than we could before. Super important. Okay. One of the challenges, though, is if you were designing a test set, you need to make sure that you've got sufficient examples to give you reliable estimates of precision. So there will be you'll get changes in the measured precision based upon the sample. This test set is just a sample. So if I sample a different subset, my precision might change. So we need to choose a kind of reasonable, error tolerance in the precision estimate that we might be happy with in production. And so therefore we need to decide, well, how many examples do we really need to give us reliable estimates? And, let's say we had 10,000 examples, 10,000 negative examples, and we were looking at a false positive rate of 10 to the minus 3. Well, that's only 10 false positives. So clearly, very small changes in number of false positives is going to make a big difference to the false positive rate, and therefore a super big difference to the precision. So one of the things we could potentially do is use a result from probability theory, Halfting's inequality, which won't go into too much detail on that, but it gives us an upper bound on the probability that the mean or on a sample and the mean on our population exceeds a certain error. And so we could decide on a threshold alpha, significance level. We could decide on a margin of error that we wanted, and we can rearrange that expression to give us a lower bound on the number of examples that we would need in order to have a level of confidence that the error will not exceed that margin of error that we've got there. And probably the most important factor for us is false positive rate, because the number of negatives vastly outweighs the number of positives. So choosing the number of negatives becomes really important to give us reliable estimates. So we can potentially use that, and we could use that inequality, and we could plot the likely error that we would see in our precision estimate against the number of samples in the negative class that we've got in our test set for a particular confidence level. So in this example, we've taken that model and our estimate is a precision of around 69%. And if we take a significance level, in this case of 10%, and use that Halfding's inequality to estimate that error, we can derive what the error will be in precision. So you can see actually very quickly we need to start to get a significant number of negative examples in order to kind of minimize that error. And at the moment our tests, I haven't put this on there, but our test data set sits somewhere around there, I think. So it's somewhere between 10 and 12.5% plus or minus error in that precision. But that may be acceptable, if it was above 50%. And you could do the same thing for the positive class as well. And obviously the impact on error is a lot smaller, and the number of samples that we require are a lot smaller as well. So some takeaways. Pay close attention to your data is probably the key takeaway here. Really think about sources of bias in your data, particularly bias in the way that data has been collected and whether there's difference in that data collection process from production. And also, is there any bias in your label generation mechanism? There often is. And I think the best way to get an understanding of that is, talk to subject matter experts within the business, or people that, if you're dealing with a production system, people that deal with that process. Most literature on class imbalance will cover class imbalance from the perspective of its impact on learning algorithms, not on its potential. And it will talk about precision and recall, but doesn't, from what I've seen, talk too much about what do you do in the circumstance like this to measure it in production. So bear that in mind. But also measuring and knowing what your positive prevalence in production can be quite difficult to do. And make sure that you've got a big enough sample in your test data set to make sure that you can make reliable estimates of precision in whatever context you're operating in. So that just wraps up that talk. Quick plug: we are hiring at the moment, so looking for 2 roles. We're working on super interesting problems, including applying LLMs to phishing email detection. Very, 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 very interesting. So feel free to come and speak to me about that if that's something that interests you. And thank you for your attention.
Amazing. That was absolutely fab. That was great, Chris. Thank you so much. Have we got any questions? Anyone got any questions for Chris?
Yes. I would ask you, how looked, let's say, if you could give several examples, how behave big fish?
How behave big fish?
Yes.
What do you mean?
Because we went through all this methodology,
Yep.
which are related to some sample, yes, generally statistical methodology. But I expect that something like big fish behave like, have some idea, and is very effective, yes, and it's not related to statistical methodology
Yep.
so much because it's rare, but it's some idea in this. Then what type of idea, which if you could tell about this, you might?
Well, I touched upon the content of the emails. So content of emails is a very strong indicator often of a phishing email, but it's not enough on its own to decide whether something is phishing. And an example of that will be something I would call conversation starters. So where you get an email, it looks like it comes from your CEO and saying, I'm at a conference, I've got an urgent task for you. You get quite legitimate emails that might look a bit like that, but they have quite a common pattern to them as well. So we're using LLMs at the moment to detect those kind of emails too. So and that would be an example where metadata wouldn't be sufficient on its own to catch those kind of phishing attacks.
Wonderful. Any other questions?
Hi. Nice talk about all the, very compliment about all the topic. I'm not a data scientist or anything like that, but I'm very interested in the cybersecurity. How would you compare what you do with Mimecast or other? Like, I mean, Mimecast is very popular, right? How would you say is doing better or worse, or how is compared to other companies?
I think in terms of the way we use behavioural data, so which is where really we started with phishing detection. So we place a particular emphasis on, impersonation is quite common in phishing emails. That could be impersonate a domain, impersonate a vendor, impersonate a person, and detect. So I send an email to you. It looks like it comes from one of your colleagues. Is that really your colleague, or is that somebody else? And that kind of, we take in the behavioural kind of interaction. So we look at, have you emailed each other before? Do we see some anomalies in the location where that email was sent to, where compared to the usual location of somebody that matches that contact information? So being able to use that kind of, I guess, full holistic sort of information is something that kind of sets us apart, I think.
Thank you.
Thank you for the presentation, first of all. So I have a question about the false negatives. So whenever you deploy the new version of the platform, do you then carry out a posteriori analysis to detect possible patterns, features in the emails that are detected as false negatives, such that they can be then incorporated in the training data set? Because I suppose that after 1 month there will be a smart large language model that can be outperform the platform, and maybe something that you have to take into account then for future releases.
That's a good question. So yes, so we have a threat intelligence team who the data science team work with incredibly closely, and one of so both teams are involved in reviewing false negative reports. So from a threat intelligence perspective, that means they can look at them through that security lens and design fast responses to those. Whereas we will look at it from a data science perspective to identify improvements or weaknesses that we've got, and actually we're involved directly in individual false negative responses, because I found that really looking at examples and being immersed in them gives you kind of context, gives you ideas about how to solve it. So yeah, that's exactly right. And as I mentioned also, every week we run our latest and greatest kind of models against those false negatives to see, how we're improving against those as well.
Brilliant. I think we'll wrap up. We've got one more question at the back, and then we'll wrap up for a coffee break.
Hi, thank you so much for the amazing talk and about the comprehensive technical details. I have two questions. First, you talk a lot about the data balance and biases. Somehow I was thinking if there is a way to enhance those levels in the sense of denoising, or more to raise the quality of the label itself. And the second question is kind of trivial. It's as you mentioned major vote, this appeared in two of the processes. I suppose, is there any alternative to the major vote, as it's might be some sort of a process for weak learning, or shall we say in some ensemble learning? Thank you.
I've forgotten your first question. I was trying desperately to remember it. Just remind me.
Yeah. Sorry. The first question is about the label enhancement.
Oh yes. Yes, I think potentially there are methods that you could use to detect label noise. There is one particular technique, and I forget the name of it off the top of my head, that you could use to detect noise in labels, and there's a Python package for that. If you're interested, I'll remind myself and look it up. And the second question around... I've forgotten. I've got a terrible memory. Oh, yes. Yeah. Alternatives to majority vote. I'd have to think about that. Probably. I think it's the sort of baseline that you could do, which is why we started with that. I think your suggestion around kind of weak learning, so I guess coming up with functions, labeling functions, could be a technique that you could do. Yes, that's sort of one thing. So one thing we have looked at is, can we identify the most reliable labelers, which is quite interesting. So look at the disparity between admins and users and build a model to predict whether a labeler is more reliable. So that's something we have looked at in the past as well.
Brilliant. Right, if we give Chris a massive, massive thank you. That was wonderful. Fab. And then we're going to break for a coffee break, back in here at 11. So feel free to go and grab coffees.